Good day, everyone. In this video, we are going to talk about the limit of a function. Here we go. If you might be wondering, in mathematics, limits are the backbone of calculus, and calculus is called the mathematics of change. The study of limits is necessary in studying change in great detail. The evaluation of a particular limit is what underlies the formulation of the derivative and the integral of a function. Let's start with the definition. Consider a function f of a single variable x. Consider a constant c, which the variable x will approach, where c may or may not be in the domain of f. The limit to be denoted by capital letter L is the unique real value that f of x will approach as x approaches c. In symbols, we write this process as this one. As you can see it here, this is the symbol of the process. And this process is read as the limit of f of x as x approaches c is L. Let's try to illustrate and consider this example. The limit of f of x, which is 1 plus 3x. So we are going to read this one as the limit of the quantity 1 plus 3x as x approaches 2. In this case, let's try to evaluate and provide table of values. In this scenario, we will be approaching 2 from its left. Yes, you heard it right. We will approach the constant c, which is 2, from its left. So if you're going to create a real number line, what's left in 2? Then that's basically 1, right? 1 is located in the left of 2. So as you can see it here in the table, we started with the first value of x as 1. And if you are wondering where does my x values came from, I am the one who suggested and created the values of x. And in this case, we have here on the right side the value of our f of x. And in order to solve for the f of x, we are going to substitute the value of our x to our function. For example, when x is equal to 1, we substitute 1 to x here in the function. Then that will be 1 plus 3 times 1, which is equal to 4. And if you would like to check the values of f of x here, 5.2, 6.1, and so on until 6.9999997, you can reevaluate and check that one using your calculator by substituting the values of x's here to our given function. And this is how the tables of values look like. And please take note that the values to be chosen should be close to 2. That is why the intervals here is very minimal from 1, 1.4, 1.7, 1.9, 1.95, 1.997, 1.9999, and it's very close to 2, the value 1.9999999, right? This is not equal to 2, but it's closer to 2. And now let's look at how it approaches from its right. So we are approaching 2 from its right. As we all know that 3 is located on the right part of 2, right? If you're going to create a number line, you can double check on that. And as we substitute the value of 3 to our function, which is 1 plus 3x. So that's 1 plus 3 times 3. That's equal to 10. And if you want to double check the other values of x's, I input here. You can double check that one using your calculator, and this will be the results. Note that the values to be chosen should be close to 2. Okay, so as you can see here, this is not equal to 2. 2.00000001 is not equal to 2, but we are approaching to 2 from the right. What have you observed from the tables? Okay, from the first table and then second table, which is this one. What have you observed? I hope we have the same observation that as the values of x get closer to 2, the values of f of x get closer and closer to 7. So you have it here. And then as we look at the other table, it is approaching closer to 7, but not exactly 7. Then our limit of quantity 1 plus 3 of x as x approaches 2 is equal to 7. So if you are wondering, sir, how will you get equally 7? This illustration here is just an assumption that the limit of 1 plus 3 of x as x approaches 2 is equal to 7. Because based on our observation from the tables, that the limit of the function 1 plus 3 of x as x approaches 2 is equal to 7. Now, let's try before another example, there is a graph here. So look at the graph. So this graph explains and illustrates as uh, as x approaches to the or as x approaches from the left. So here you start with 1 and then 4. So you have it here 1, 4. So this is the first plot. And then 1.4, 5.2. That's in this point. 1.7 and then 6.1 this point, 1.9 and 6.7 here, and then they are closely plotted until they reach 7 because the value of our C is 2, and then the limit as we assume is 7. So you can see it there that as you can see in this plotted graph, the point is 2, 7. And we have the same face or the same can be seen from the right. So if we start from the right also, it will also look like this one. And let's investigate another example. The limit of the quantity x squared plus 1 as x approaches negative 1. By constructing tables of values, here c is equal to negative 1 and f of x is equal to x squared plus 1. We start again by approaching negative 1 from the left. So if you might be wondering if why are there 4 values of x only? Yes, it's all right. You can have at least 3 or 2 and above values of x to plot, which is nearer to your C. Since our C here is negative 1, from the left, you have negative 1.5. If you're going to locate that in a real number line, negative 1.5 is located from the left. And substituting the value of x to your function, you are going to get the value of f of x, which is 3.25. And when our x is negative 1.2, the value of our f of x is 2.44. Same goes for the other values here below. Now, approach -1 from the right. As you can see here, since the value of our C is -1, then -0.5 is located from the right. Yes, -0.5 is greater than -1. Therefore, we can say that it's located from the right since we are on the negative values of our x. So if you're going to substitute this value, you will get this value as our f of x. And if you can also double check the other values, you will get the same values here as I've plotted in my tables. And the tables show that as x approaches -1, f of f of x approaches 2. As you can see, the value 1.999800001, that's very close to 2. So in symbols, the limit of the quantity x squared plus 1 as x approaches -1 is equal to 2. There you go. And to graph that table from our second example, it will look like this. So it is a parabolic graph. So let's start with negative 0.5. So it is uh, negative 0.5. It is here, negative 0.5 from our x. So this is 0 and this is -1. This is negative 0.5. So it's located in this black portion. And then negative 0.8 is 1.64, so it's increasing, and then it's increase what I mean, the value is not uh the value of x is not increasing, but the value of our f of x is increasing. That's why it is going upward. Mm. So this is how the graph looks like from the function x squared plus 1. This is the graph of the limit of the quantity x squared plus 1 as x approaches -1. So here is the plotted point, -1, 2. The same can be seen from the left. So we will have the same phase if we are going to plot the tables from the left. We have another example. Estimate the value of the following limit. You might be wondering, why did I say estimate? Because we are just using table of values. So I am the one who assumed the values of x, which is not really given, because I am just trying to uh, balance it well where it might reach the certain value of our c, as you can see here as x approaches 2. Therefore, let's read first the given. The limit of x squared plus 4x minus 12 all over x squared minus 2x as x approaches 2. Look at our function. The function is in a Yes, it is in a rational form. We cannot plug in x is equal to 2 because it will make the function undefined. Yes, we will still follow that rule of rational functions that the denominator should not be equal to 0 because it will make the function undefined. If you're going to try and plot or plug into here in our x, let's check the denominator. So that's 2 squared, which is 4, minus 2 times 4. So that's 4 times 4, which makes it 0, and that makes the function undefined. But we can still plot the tables, but we are not going to include 2. So here is how you're going to plot from the right and then from the left. So you can really enumerate them. From the right of 2, we have 2.5. We start with 2.5. And then from the left of 2, we start with 1.5 closer to 2. And from the right, that's 2.5 closer to 2, but not exactly 2. So if you're going to double check on that one, the value of our x, and whether my f of x here is correct or not, you can check it on your calculator. Same goes from the left. The value of x is here, and then here is the value of our f of x. So I chose 6 values, as you can see here, 2, 4, 6 values of x to really graph it accurately. From this table, it appears that the function is going to 4 as x approaches 2. So the limit of x squared plus 4x minus 12 all over x squared minus 2x as x approaches 2 is equal to 4. And that's our answer. And here is how the graph looks like. First, notice that there is a rather large open dot as x is equal to 2. This is there to remind us that the function and hence the graph does not exist at x is equal to 2. That's why we use a hollow, which means it's not shaded because uh, this value of x is not part of the function or will make our function undefined. So this is how the graph looks like. Since it is a rational function, it is asymptotic. So if you're going to continue that value there, going up and going down, it's somehow asymptotic because it's a rational function. Now, let me ask you the question, does it apply to all that given a limit of a function as x approaches to c, the answer is f of c. And then you need to state why. Then, here is an example. The limit of our f of x as x approaches c, for example, the limit of x squared plus 1 as x approaches negative 1, this is equal to 2. Therefore, substituting our negative 1, f of negative 1 is also equal to 2. This is really amazing. How about on this function? Limit of the absolute value of x as x approaches 0 is equal to 0, and f of 0 alone is equal to 0. Are we going to say yes or no for this question? We must not decide yet. Even though it applies here, let's try to look at this function. Given f of x is equal to the absolute value of x if x is not equal to 0, and f of x is equal to 2 if x is equal to 0. Therefore, the limit of our f of x as x approaches c, for example here, as x approaches 0, the limit of the absolute value of x as x approaches 0 is equal to 0. But our f of 0 is equal to 2 based from this piecewise function. And we can say that it is not applied here. Therefore, we can also confirm that it does not apply to all that given a limit of a function as x approaches to c, the answer is f of c. Let's proceed to the next topic, which talks about the limit theorems. Yes, we have also theorems here to consider in limits on how we evaluate limits alone. Starting with the first theorem. The first theorem states that the limit of a constant is itself. If k is any constant, then the limit of k as x approaches c is equal to k. And that is really the first theorem. And please take note for this theorem because it is very applicable to all examples or to other examples. For example, we have here number 1, 2, and 3. We have three examples. The limit of 2 as x approaches c is equal to 2 as we apply the first theorem, which is the limit of a constant is itself. And then the limit of negative 3.14 as x approaches c is equal to negative 3.14. And then the third one, the limit of 789 as x approaches c is equal to 789. Yes, it's still very easy here to apply the limit of a constant. Now let's try the second theorem. The limit of x as x approaches c is equal to c. This may be thought of as the substitution law because x is simply substituted by c. In other book, they call it, and they name it the identity theorem. If given a limit of x, where x approaches c, it's just equal to c. So this is our second theorem. Let's observe some examples below. The first example, the limit of x as x approaches 9 is equal to 9, which is the value of our c. And then the limit of x as x approaches 0.005 is equal to 0.005. And for the third one, the limit of x as x approaches negative 10 is negative 10. Yes, it is still very simple on the first and the second theorem. How about this one? For the remaining theorems, we will assume that the limits of f and g both exist as x approaches c and that they are L and M respectively. In other words, the capital letter L and M represents the limit. So you can see it here below. The limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is M. And we will be using here for the rest of the other theorems. Let's start with the constant multiple theorem. This says that the limit of a multiple of a function is simply that multiple of the limit of the function. Mhm. You may be thinking it sounds like repeating. No, please try to read and comprehend it well. This theorem says that the limit of a multiple of a function is simply that multiple of the limit of the function. And this is how it looks like. The limit of k times f of x as x approaches c is equal to k times the limit of f of x as x approaches c, which is equal to k times L. And this is how we familiarize this theorem, the constant multiple theorem. Let's try to observe some examples. For example, if limit f of x as x approaches c is equal to 4, then for example, number 1, finding the limit of 8 times f of x as x approaches c is equal to 8 times the limit of f of x as x approaches c, which is this one, 4. We will substitute 4 here, and that's 8 times 4, which is equal to 32. Because we already have a given limit function above. We'll just simply substitute it to our equation. For the second one, the limit of negative 11 times f of x as x approaches c is equal to, it's like extracting out first the constant negative 11. From this case, uh, we are going to extract it or place it here on the first part. So negative 11 times the limit of f of x as x approaches c, which is 4. So we replace this one by 4, and that's equal to negative 11 times 4. And that's negative 44 for the second example. For the third example, the limit of 3 over 2 times f of x as x approaches c is equal to 3 over 2 times the limit of f of x as x approaches c, and we substitute the value of our limit function, which is 4. That's equal to 3 over 2 times 4. 3 times 4, that's 12, divided by 2. The answer is 6. Now let's have another theorem, the addition or subtraction theorem. The theorem states that the limit of a sum of functions is the sum of the limits of the individual functions. And then the limit of a difference of functions is the difference of their limits. So they are just the same with the sum. The sum and difference are just the same with each other. So you are going to illustrate that here below. So this one is the addition or the sum, and then this is the subtraction theorem, the second one. Let's observe first the addition theorem. The limit of the quantity f of x plus g of x as x approaches c is just equal to, we're going to distribute the limit function to the limit to each function. So that's the limit of f of x as x approaches c plus the limit of g of x as x approaches c is just equal to L plus m. And then for the subtraction one, they apply the same rule, but the only difference there is their operation, which is subtraction. Let's try an example. For example, if the limit of f of x as x approaches c is 4, and the limit of g of x as x approaches c is negative 5, then for the addition, the limit of f of x plus g of x as x approaches c is equal to the limit of f of x plus the limit of f of x as x approaches c plus the limit of g of x as x approaches c is just equal to 4 plus negative 5, and that's equal to negative 1. We apply here the basic rule, which is the rules of integer is very useful in this case. And for the second one, it is in a difference now. So we apply the same. Just the sign, the sign is just changed. So the same substitution for minus negative 5. Applying the rule of subtracting integers, we change the operation and then the sign of negative 5. From negative, it will be positive, or we simply apply negative and negative will turn out positives. That's 4 plus 5, and that's equal to 9. There you go. How about the multiplication theorem? The theorem states that the limit of a product of functions is equal to the product of their limits. So it is illustrated like this. The limit of f of x times the g of x as x approaches c is just equal to the limit of f of x as x approaches c multiplied by the limit of g of x as x approaches c is equal to L multiplied by m. And let's observe some examples. Again, let the limit of f of x as x approaches c is equal to 4, and the limit of g of x as x approaches c is equal to negative 5. Then applying the multiplication theorem, you are going to see it like this. Just the same, the limit is distributed to each function, and it will look like this. And then substitute the given, we have 4 for f of x and times negative 5 for the g of x, which is equal to negative 20. How about the division theorem? The limit of a quotient of functions is equal to the quotient of the limits of the individual functions where the denominator limit is not equal to 0. And it is illustrated like this. The limit of f of x all over g of x as x approaches c is equal to the limit of f of x as x approaches c all over the limit of g of x as x approaches c is just equal to L O over m, provided m should not be equal to 0 because it will make our answer undefined. That's for the division theorem. Let's try an example. If the limit of f of x as x approaches c is equal to 4, and then the limit of g of x as x approaches c is equal to 5, a negative 5, we apply the division theorem. How are we going to solve this one? We do it like this first, and then we find the limit of the denominator first, followed by the I mean of the numerator first, followed by the denominator, which is equal to 4 as we substitute the value, and then negative 5 for the denominator, and that's equal to negative 4 over 5. Following by another example. If the limit of f of x as x approaches c is 0, and the limit of g of x as x approaches c is negative 5, then applying the division theorem, 0 over negative 5 is equal to 0. Yes, it is okay if the numerator is 0, but it's not okay when our denominator is 0 because that will makes it undefined. But in this case, this is just equal to 0. Number 3. If the limit of f of x as x approaches c is 4, and the limit of g of x as x approaches c is 0, then this is a big question. It is not possible to evaluate the limit of f of x all over g of x as x approaches c because the limit d and e or does not exist, which means why is it does not exist? Because it will make it the limit will be undefined. Now let's have the power theorem. The power theorem states that the limit of an integer power p of a function is just the power of the limits of the function. And this is how the solution or the formula looks like. The limit of f of x raised to the power of p as x approaches c is just equal to the limit of f of x the limit of f of x as x approaches c raised to a power p, that's simply L raised to the power of p, raised to the power of p. For example, if the limit of f of x as x approaches c is equal to 4, then how about if this limit is raised into cube? The limit of f of x raised to the power of 3 as x approaches c is just equal to, we are going to cube the whole expression itself, including the limit. So that's the limit of f of x as x approaches c raised to the power of 3 is just equal to 4 raised to 3 or 4 cubed, and that's equal to 64. You can double check it by 4 times 4, which is 16, times 4, that's 64. Another one. If the limit of f of x as x approaches c is 4, then if we are going to raise it into negative 2, we are going to apply the same process, raise it to negative 2, then 4 raised to the power of negative 2 is equal to 1 over 4 squared, and that's equal to 1 over 16. If you might be wondering, we are applying here the loss of exponent. If we have a negative exponent, then we can simplify it by placing it on the opposite side. So if the negative power is located on the numerator, then we can change it into the denominator's position. If it's located in the denominator, we can change it into the numerator's position. But in this case, since this is 4 raised to the power of 2, that's automatically over 1. So this is in the numerator, then we are going to simplify it like this. 1 over 4 squared, and that's equal to 1 over 16 because 4 times 4 is 16. Now we are here in radical root theorem. The theorem states that the limit of the nth root of a function is the nth root of the limit of the function, provided the nth root of the limit is a real number. If n is even, the limit of the function must be positive. Yes, you're going to follow this given theorem, and this is how it looks like. The limit of the nth root of f of x as x approaches c is just equal to the nth root of the limit of f of x as x approaches c, which is equal to the nth root of L. So it's really nice. I really love the radical theorem because it's very amazing how you apply the radical expression, right? The rules of how we manipulate the operations of a given radical function. For example, if the limit of f of x as x approaches c is equal to 4, then the limit of the square root of f of x as x approaches c is equal to the square root of the limit of f of x as x approaches c, and that's equal to the square root of 4, which is 2. We have the second example. If the limit of f of x as x approaches c is equal to -4, then it is not possible to evaluate the limit of the square root of f of x as x approaches c. Why? Because as you can see, as we substitute the value, it is not a real number. We are negating the definition of how limit is. And it is clearly stated in the definition. Let me go back here. Provided the nth root of the limit is a real number. Okay, so if you're going to encounter example number 2 like this, just simply write not a real number. Now, let's proceed to limits of algebraic functions. Let's start with example number 1. Determine the limit of 2x plus 1 as x approaches 1. For the solution from the theorems above or from the theorems mentioned, we will be applying that here, or we will be applying them here. Starting with this one. The limit of 2x plus 1 as x approaches 1 is just equal to the limit of 2x as x approaches 1 plus the limit of 1 as x approaches 1. We are applying the addition theorem for the first solution. And next to addition is we are going to apply the constant multiple. Why? As you can see, we have a constant 1 already here, right? And then that's the limit this in this case the constant multiple also is 2. We also have 2 here, so 2 the limit of x as x approaches 1 plus 1, therefore it's equal to 2 times 1. This in this case this is 1 alone because the value of our x is 1, the limit of 1 is just 1, right, plus 1, and that's 3. Let's have another example. Evaluate the limit of the quantity 3x raised to the power of 4 minus 2x minus 1 as x approaches 0. For the solution, we started it with a subtraction. Look at the operation. It's a subtraction operation. So the first one is separate each term applying subtraction theorem. So now, as once we're done separating them, we are going to proceed with constant multiple. As you can see there, there's a constant 3 from the first term. There's a constant 2 from the second term. And then the limit of 1 as x approaches 0 is already 1 because of the constant 1. And then the 3, after constant multiple, we proceed with this one, applying our power rule. So 0 raised to the power of 4, so that's within the limit. minus 2 times, that's 0, because 0 squared alone is 0, right? And then minus 1. Next, that's 0. As we simplify it, 0 minus 1, that's negative 1. And that's our answer for this function. And we evaluate the limit of the quantity of x minus 3 times the quantity of x squared minus 2 all over x squared plus 1 as x approaches 1. First, we check the denominator because this is a rational function. So the denominator itself, so we check it first if it will not be equal to 0. Applying addition rule, so we separate x squared and then 1. That's equal to 1 plus 1, which is equal to 2, and 2 is not equal to 0. Then we are safe in this given. We are good to solve this one. Solution starts here, guys, and that's applying division first because it's a rational function, so we apply division. So the limit of the quantity x minus 3 times the quantity of x squared minus 2 as x approaches 1 all over the limit of x squared plus 1 as x approaches 1. After that is the multiplication. As we go, we multiply it like this. The limit of x minus 3 as x approaches 1 times the limit of x squared minus 2 as x approaches 1 all over 2. Why is it all over 2 already? I already simplified the denominator as x approaches 1, so I substituted 1 here. 1 squared plus 1, that's 2. And then next will be the subtraction. So we subtract this term and this term. Then we apply the limit of x as x approaches 1 minus the limit of 3 as x approaches 1 times the limit of x squared as x approaches 1 minus the limit of 2 as x approaches 1 all over 2. After that, we simplify. This is 1 minus 3 and 1 squared minus 2 all over 2. 1 minus 3, that's negative 2 times, that's 1 minus 2, right? Which is also negative 1. Negative 2 times negative 1, that's 2 all over 2. That's equal to 1. And this is how we solve this given limit of a function. And that ends our discussion.